Alright, hello everybody, and this is the 10th video in my calculus series. In this video, we're just going to be reviewing some of our derivatives before we move on to some other spicy stuff. So let's say, for example, we want to take the derivative of, 3 square root of x to the third power. How exactly can we do that? Well, remember, by one of the derivative properties, we can bring this 3 out to the front, just like a constant, and we can just differentiate this function here. But notice this thing looks kind of ugly because we have the square root here, but in fact we can turn it into a power, because remember, the square root of something is just that something raised to the 1/2 power. So this is equal to x cubed but raised to the 1/2 power. That's exactly the square root. And you see we have a power to a power, so we can actually multiply those together to get 3 times the derivative of x to the 3/2 power. And then here, notice we can use the power rule for that. So just bringing this power down to the front and then reducing the power by 1. What exactly are we going to get? Well, we're going to get 3, and then bring this power down to the front. We're going to get 3/2 x to the 3/2 minus 1. But notice 3/2 minus 1, that's exactly 1/2. So we're going to get this in the end. And then x to the 1/2, that's exactly the square root of x. And we can clean things up in the front right here to get 9/2 square root of x. And this thing right here is the derivative of this other function right here. And let's say we wanted to find the gradient of this function at the point, let's say x is equal to 5. How exactly can we do that? Well, remember, the derivative, whatever function we get out the ends right here, this function helps us to find the gradient at every single point on our original function. So if we want to find the gradient of this function at the point x equals to 5, all we really need to do is plug 5 into this function right here, because this function gives us the gradient. So if we do that, the gradient at the point x equals to 5, that's exactly 9/2. Plugging 5 into here, that's going to give us root 5. So 9√5/2, this is exactly the gradient of this function at x equals to 5. Alright, so for the next example, imagine we have some car, and its displacement, or its distance it has traveled, can be modeled by this function f right here. So we have f of t being equal to 1/9 t cubed, where our t, or our time, is greater than 0. So remember, as I said before, f will give us the distance. So this function, depending on what time we choose, if we plug that time into this function, we're going to get out another number that tells us how far we've traveled. And our question is, what is our speed after 4 seconds? So how exactly can we do that right here? Well, if f is a distance versus time function, maybe we can differentiate this to get a speed versus time function. Because remember, the derivative is comparing a change in the output over a change in the input. And our output in this case is distance, our input is time. And remember, distance over time is speed. So maybe if we want to find a function for the speed of a car, it would be nice if we can differentiate this. So let's write f prime of t. Remember, f prime, all that means is the derivative of f of t. And that's exactly equal to, well, we want to differentiate this thing right here. So we want to differentiate not with respect to x, but with respect to t, because notice t is the variable we're interested in. So we're going to have the derivative of 1/9 t cubed. We can bring that 1/9 out to the front and just differentiate this t cubed right here with respect to t. And that's going to give us 3t squared just by the power rule. Bring this power down, we're going to get a 3. Reduce the power by 1, we're going to get a 2. And this cancels out nicely to be 1/3 t squared. So this thing right here, that's exactly our f prime of t, being equal to 1/3 t squared. And if we want to find the speed of our car at the time t equals 4, all we need to do is plug 4 into our speed function right here. So f prime evaluated at the time equals 4, that's going to give us 1/3 4 squared, that's 16. And that's going to be 16/3. So 16/3 is the speed of our car at the time t equals 4. Alright, so for the next example, we have this ugly looking thing right here, and we want to find the stationary points of this function. So first of all, let's break down what this thing right here actually means. So first of all, we have our function f of x, which is this part right here. And notice that's just some cubic right here. And looking at our domain, notice this first part right here. All that's saying is that we're just taking in positive values of x. So r plus just means positive real numbers. So this function only exists in the positive x-axis. So we want to find the stationary points of this thing. And to do this, we can actually use differentiation to do that, because remember, the derivative tells us the gradient of our function at every single point. And what's a key feature of a stationary point? Well, a stationary point, notice that it has a gradient of exactly 0. So if we can differentiate this function right here, we can use that function and find where it equals to 0, because wherever it equals to 0, our original function will have a gradient of 0 and therefore a stationary point. So enough talking, let's just get straight into it. So we want to calculate f prime of x. And you see this thing right here, we can just break it up into multiple derivatives and use the power rule on each one. So first of all, x cubed, the derivative of that just using the power rule, that's 3x squared. And then we're going to have a minus derivative of 2x squared. We can ignore this 2 for now and think about the derivative of x squared. Well, that's just 2x. And multiplying this 2 back in, we're going to get negative 4x like so. Derivative of this lonely x right here, that's going to be 1. So this function right here, f prime of x, will help us find the gradient at every single point of our original function. But the thing is, we want to find stationary points. So we want to find where this function gives us a value of 0. So why not set this function equal to 0? So we have 0 being equal to 3x squared minus 4x plus 1. And you see, now we have a nice quadratic and we know how to find the zeros of this thing. Why not use the quadratic formula? So we have our b value right here, our a value and our c value. So that means x is equal to, while using quadratic formula, we have our negative b. So negative 4, that's 4, plus or minus the square root of b squared, negative 4 squared is 16, minus 4, a which is 3, c which is exactly 1, so square root of all of that junk, and we're dividing everything by 2a which is 6. Alright, nice and fine. 4 times 3, that's exactly 12, times 1, that's also 12, so we have 16 minus 12 in here, but 16 minus 12 is 4, so we're going to have 4 plus or minus the square root of 4, but the square root of 4 is nothing but 2, and then we're going to divide everything through by 6, and simplifying this a little bit, we're going to get 2/3 plus or minus a third. So what are our two solutions for x? We have x being equal to 2/3 plus a third, which is exactly 1, as well as x being equal to 2/3 minus a third, which is exactly a third. So those are our two solutions right there. And the nice thing about these two solutions is that they're both positive. So these two are both valid solutions for our domain right here. So if we had negative solutions for x, then we would only take the positive one, because this is our domain right here. So what does this mean right here? These 2 points are where our derivative equals to 0. And remember, the derivative tells us the gradient. So pretty much these 2 points are where our gradient of our original graph equals to 0. And wherever our gradient is 0. So if you imagine we have some weird looking graph or something right here, wherever the gradient is 0. So here, those are all stationary points, because the graph isn't changing up or down or anything, it's just stationary. So these points right here, 1 and 1/3, those are where our original function doesn't change, so it's where our stationary points exist. And notice it says points right here, so we kind of have to figure out the corresponding y values. So to do that, it's pretty straightforward. We just sub these values into our original function. So first of all, we have f of 1 being equal to, well, 1 cubed is 1, minus 2 times 1, which is 2, and then plus 1, and all of that just evaluates to 0. So our first point is 1, 0, and plugging a third into here, so f of 1/3, that's exactly 1 over 27 minus 2 over 9, plus a third, and well, that's 27, 6, and 27, 9. 9 plus 1 is 10, minus 6 is 4, so we have 4 over 27. So 1/3, 4 over 27, that's our second stationary point for this function right here. So yeah, that's pretty much it for this video on just a little bit of a review of derivatives and a little bit of application. So yep, hope you guys enjoyed, and I'll see everyone next time for some more spicy calculus stuff.